evening, everyone. I welcome you all in the sixth live session of the NPTEL course Symmetry and Group Theory taken by Professor Anindya Datta. I am Shruti. I am a PhD student in the Department of Chemistry, IIT Bombay, and I am the TA for the course. So today we are discussing assignment for the fifth week. So let's start. The first question is, a molecule contains the following symmetry operations: E 2C6, 2C3, C2, 3 sigma D, 3 sigma V. The number of classes and order of the symmetry point group is. So we need to find the order and we have been given the symmetry elements. So order of a point group Hello Parimal, have you solved the fifth assignment? Did you get all the answers correct? Or there is some confusion?
Some answer have been.
Yeah, that I know. There are two questions with wrong answers given, but apart from that, everything is fine.
Yes, ma'am.
There's only 7 questions, and I think those are pretty easy.
Yes, ma'am.
Yeah, okay.
Sure.
So I was telling what is order, and it is denoted by the symbol H. Order is defined as the total number of symmetry elements, symmetry operations, not elements, symmetry operations that are there in the group. So symmetry operation means the number of ways we are transforming the molecule so that we get the indistinguishable or equivalent configuration. That is number of ways the molecule can be transformed to get an equivalent configuration. So order can be 1 or order can be 12, 24 or many for any point group. Now let's come to class. Class is denoted by this symbol K, and till now what we have learned is class is the group of symmetry operations which are conjugate to each other. So set of symmetry operations within a point group So what it does, set, each class each class preserves a specific element of the molecule. So in, suppose we have a group of G6, then we saw there were three classes E, A, B, C and D, F. Okay. So each of these class preserve one specific element in the class. In the symmetry operation of this molecule, whosoever point group will be G6. So class represents okay. So here we saw in this example, it is specifically written as a set of class. So in this one we have E2C6, C3, C2, sigma D and sigma V. So these are written as a set of class. So we have how 1, 2, 3, 4, 5, 6. So we have 6 classes. And order will be the sum of number of symmetry operations. So order will be 1 plus 2 plus 2 plus 1 plus 3 plus 3 sigma D. So order will be 12 and class will be 6. So the correct answer will be C. Okay. So the next question is symmetry point group of 1,3-dichloroalane is. Now we have to find. Now we know alene, simple alene. The point group is, what is the point group of an alene? Parimal, are you there?
Yes, ma'am.
Yeah. So simple alene in which all the substituents are same. What is the point group?
C2H.
No, it is D.
Okay, D2H.
D2D.
Okay.
So let me show you. I think I have shown this earlier also. This is an alene, isn't it?
Yes, ma'am.
So it has a C2 which passes through this. So C2 is this is the principal axis passing through the maximum number of atoms. Otherwise, there is one C2 from here as well. So this one. Okay. So this is the principal axis and two more C2s perpendicular to it. So it is a D point group. And then we have sigma planes. So we have sigma plane along these. So this is so these are the two planes containing both the groups. So one is this one and the other is this one. So this is a dihedral plane because it is bisecting the C2 axis. So it is the angular bisector of both C2s. That's why it is a D plane. Okay, so the point group is D2D for the simple alene. So all these substituents are same. But now in this question, they have changed the trans atoms. So here one is chlorine, suppose this one, and this one is chlorine. So what are the elements we will be left with? So if this is a chlorine, so just now I showed. So this is the sigma plane. So let me show only one. Okay. So this is a plane. Okay. Now this is a chlorine, this is a hydrogen. So this plane is gone, right?
Yes, ma'am.
Okay.
Sigma D is left out.
So sigma D is not there. Now
Yeah.
similarly, this is chlorine, this is hydrogen. So this plane is also gone. So
Yes,
sigma
ma'am.
D is not there in this one. Now S4. So suppose S4. Let's see. So S4, it has to turn by 90 degree and then go to the perpendicular and then get reflected by this perpendicular plane. So let's see like this. Now suppose this one is chlorine and this one is chlorine. You can see my cursor, right?
Yes, ma'am.
This is chlorine, this is chlorine. Okay. So, okay. So this one is following. S4 is there, but when you do S4 inverse, is it following? S4 inverse won't work. So S4 is also gone.
Yes, ma'am.
Okay. So we are left with C2. And okay. So this principal C2 will be there. This C2 will be there.
Mm.
Suppose, yeah. Okay. Now let's see how it is turning. This one is chlorine, this is chlorine, 1 and 3 positions. So let's see. Okay.
Not following.
Not following. Okay. So
Mm.
this C2 is gone. Now let's see the other C2. Let's follow one. Okay, this one. This is correct.
Mm.
See only one atom, maybe this one, and then follow it. See like this, maybe you can visualize better. This is following, right? See this one, and this one should be chlorine. Okay, now
Yes,
let's
ma'am.
see, this has to come in place of this, not following, right?
Yeah.
This is going here.
Only one C2 is following, ma'am.
Okay, now let's see the other one. There should be something. Now this is coming here. Now only this C2 is left. Okay. So
Okay.
out of, when you change the two groups from D to D, the symmetry reduces to C2. So this is for normal allene, and for this trans disubstituted it is C2.
C2.
Now the third one is, the non-polar molecule can never have the point group. So non-polar molecule means the dipoles should get, or dipole moment should get cancelled away. Okay, so because of the symmetry of the molecule, the dipole moment should be on the opposite side and they should get cancelled. So that then the molecule will be a non-polar molecule. Now let's see the first one, C infinity V. Can you give an example for this? C infinity V?
Linear molecule.
Linear
CO2.
molecule. Yeah, right. Linear molecules. Is H2 an example of this?
Yes, ma'am.
No, no. There is a condition. Linear molecule without center of symmetry means unsymmetrical linear molecule.
Okay. HCl means.
Yeah. So this should, so H2 has a center of symmetry, right?
Yes, ma'am.
So H2 is, H2 belongs to D infinity H.
Okay.
So for C infinity, you can imagine all the uh, heteronuclear kind, diatomic kind of molecules.
Okay. HCl has acid.
Yeah, yeah. sp hybridized. Now, so let's see. Can you give an example now?
CO2 and HCl.
What?
CO2 and HCl.
CO2 will again be, HCl is fine. CO2 will be again symmetrical, right?
Center of symmetry there.
Yes. So HCN
Yes.
is fine. HCN is, if we write it like this, which is not correct, it is ionic. Okay, so let's see. HCN will take. Now, since the groups are dissimilar, the dipole will not get cancelled away, right? Suppose one more example, CO. Instead of CO2, I am taking CO. So CO is also, the dipole will be like this. There is nothing on this side to cancel it. Okay.
Okay.
So this kind of molecule, can it be non-polar?
Partially charged are there, ma'am.
Think in terms of symmetry. I know charges are there. This is also not covalent. This is ionic. But think in terms of this. Given the point group C infinity V, can we say the molecule will be non-polar? What are the conditions?
No.
So it should lack center of symmetry, right?
Yes, ma'am.
So if center of symmetry is not there, the dipole moments will not get cancelled away anyway. So suppose
Yeah.
there is one dipole like this, one dipole should be like this to cancel it. Okay,
Yeah.
net will be zero dipole. So if there is one dipole like this one is like this, so the resultant dipole will be somewhere here. So there should be one equivalent dipole like this to cancel it. Okay. So the
Okay.
molecules which have center of symmetry cannot be polar.
Sure.
Okay. So the question asking is, a non-polar molecule can never have a point group. So this is true. A
C
molecule which
infinity.
is non-polar can never have a point group C infinity V. Now let's check the other ones also. The next one is D infinity H. Now, whichever you told before, CO2, H2, N2, these are all in the D infinity H group.
Infinity. Yeah.
So their dipoles will get cancelled. There is no net
Sure.
dipole.
Yeah.
So this is non-polar, and a non-polar molecule can have D infinity H. Now the next one is tetrahedral. Okay. So now tetrahedral can, like in allene, here, like this, all four groups are different, right? So if I write methane like this, then it is non-polar.
Yes, ma'am.
But if okay, point group will change. Okay, so whichever has tetrahedral, okay, take the case of, okay, let it be. So if I'll write like this is also non-polar. So because it has a center of inversion I present, the dipoles will get cancelled away.
Nice.
So a non-polar molecule can have tetrahedral, and similarly it goes with octahedral,
True.
because yeah, center of inversion is present, so a non-polar molecule can have octahedral point group as well. Like this, if all the groups are same, okay, so this one is also non-polar. So the correct answer is first one itself, C infinity V.
Yes, ma'am.
Yeah. Now for ferrocene, upon changing the conformation from staggered to eclipsed, following symmetry elements are lost. Now there is a problem in this question. So it is saying from staggered to eclipsed. Now let's see. Staggered ferrocene. What is the point group?
Uh,
So it will be staggered like this. Two pentagons kept twisted
yeah.
by a angle of 36 degrees, I think. So what is the point group for this one? I think eclipsed one is fine, right? What is eclipsed?
Same angle.
Yeah, same angle,
Seven
but
mm.
what will be the point group? The other one is also over this.
D D5D eclipse में होगा मैम.
Eclipsed is D5H because this has a plane, right?
हाँ, yeah. D5H, yeah.
D5H. And D5D is this.
Yeah, okay.
Okay, let me show. This is ferrocene. Okay.
Yes,
CP
ma'am.
ring and this brown color is iron atom.
Yeah.
Now C5 is easy.
Yes,
C5
ma'am.
passes through this, through the ring and cutting
Ferrocene.
the F atom. Okay.
Yeah.
Like this. So this is C5. First element we have found is C5. Now let's write here C5. E will be there always, right?
Yeah.
C5E. Now we are left with 5 C2 rotations.
Yeah, that's true.
So let's see one. Can you see the C2? It is exactly parallel to these two H atoms, but
Yeah.
it is passing through the iron.
I know.
Okay.
Yeah.
Now see 180-degree rotation out of
Yes, ma'am.
plane. Okay, so similarly, there are five pairs of hydrogen, so there will be 5 C2s. Like one will be like this, another will be like this. So we have
5C2.
5 C2s. Now there is an S5 as well because it has a plane. Now let's see the plane first. This is the plane. You can see it
Sigma.
reflects exactly. Sigma
Yeah.
H because
Yes.
C5 was perpendicular to it.
Yeah.
Okay. Now
Okay.
since C5 was there and it has a sigma H, so there is S5 as well.
Yes, ma'am.
Okay, because all the atoms are same, so it can rotate by 72 degrees and then get reflected by this plane. So we have sigma H and S5.
S5.
Also, inversion is there
Yes.
because it is inversion will be the iron atom. Okay.
Mm-hmm.
Okay. And then along all the C2s, there will be planes as well. Not along the C2s, like bisecting two C2s.
Yes, ma'am.
Okay, so this one I can remove. Okay, so like this you can draw 5 planes. One,
Yeah.
2, 3, 4, and 5. So there
Yeah.
are 5 planes as well. So the point group becomes D5H because sigma H is there. Now
Yes,
see
ma'am.
the staggered. In staggered, E will be there, C5 will also be there, because if you consider the top one, if you will rotate the top one by 72 degrees, the down one will also get rotated, and it will come to
Yeah.
the same position, because
Yes, ma'am.
there is no change in the atoms. Only the first ring is rotated by 36 degrees. So C5 will be there.
Yes, ma'am.
Now what we saw, S2, sorry, C2. Let's see. Okay, we saw C5,
Yeah.
and similarly, exactly through C5 we have S10. There is no S5 because S5 meant that exactly on top of one ring the other ring should come. That was the meaning of S5 in case of the eclipsed configuration. But here you see there is two rings of the top, two carbon of the top, and there is a in middle there is a carbon atom of the bottom ring. So this has to, this angle between, okay, let me, so this angle like this, if I want to, this angle, can you see my cursor? So this angle will be how much?
Mm-hmm.
The angle between these two, it was 72. Okay,
Okay.
360 by
Yeah.
5, 72. So it is half of 72, or 360 by 10, 36. Okay, so
Yeah.
you
Yeah.
have to rotate it 36-degree and then reflect it.
S10.
So it is S10. You got it?
Yeah. Yes,
So,
ma'am.
so we have S10, but plane is lost. There is no plane.
Yeah, sigma H
Sigma
lost.
H is lost because of the twisting. So we have S10, but sigma H is lost. Now C2 we will see. Okay, let's visualize I, inversion center. Now if you go top from Fe to this side, and if you go on the opposite side like this, you will find another atom. Okay, let's see. So you are going in this direction and then you are going in this direction, you will find this. If
Yes,
you are
ma'am.
coming this atom through Fe, then you will find this atom. From this top to Fe, then down, you will find this atom. So inversion is still there, and
Yeah.
inversion center is this iron atom.
Yes, ma'am.
So we still have I. Now this figure, it shows sigma d's.
Yeah.
Okay, you got this?
Yeah. Yes, madam.
There are still 5 sigma d's.
Yeah, ma'am.
The twisting is not does not matter here, because so if this conal angle, if you see, now here we have this one, so it is exactly reflecting. It doesn't matter whether this was here or it came here.
Yes, madam.
So sigma d, all 5 sigma d's are there, and likewise the c2s are also there.
Yes, madam.
Okay, so we have sigma d and c2.
Yeah.
So now the
Five.
question is asking, from staggered to eclipse, if we go
Okay.
here, what we are losing?
S10 and
We are
sigma h.
losing, yes, S10 we are losing. No, sigma h we are not losing. Sigma h we are
Yeah,
gaining,
sigma
because,
h. Okay. Okay.
yeah, sigma h was not here first. So
Mm-hmm.
the answer should be S10.
S10.
Yeah.
Yes, ma'am.
And if you go reverse from eclipsed to staggered,
And S5 and sigma h lost.
yes, S5 and sigma h will be
Sigma.
lost. So this is the wrong answer given, right? The answer actually given is uh, these two, C and D. But D won't be the answer, it will be C only.
Yes, ma'am.
So the fifth one is, traces or characters of transformation matrices for clockwise and anti-clockwise rotations are equal, reciprocal, negative, negative reciprocal. So what should be the answer?
Equal to each other.
Why? Why the traces are equal for clockwise and anti-clockwise?
I think C2V.
Yeah, think of C2V.
Hmm.
Okay. Now, what clockwise and anti-clockwise? When we write the transformation matrix, first of all, how we calculate trace or character? What is the trace? Trace or the character of a symmetry operation is calculated from the transformation matrix of that symmetry operation. Okay, every symmetry operation will have a transformation matrix. Do you agree with me?
Yes, ma'am.
Yes. So if there is a matrix, there will be diagonal elements and off diagonal elements.
Yes.
So trace is what? Sum of the diagonal elements.
Okay.
Sum of the diagonal elements, we call it trace or the character. Okay.
Oh. Yes, ma'am.
So now for clockwise and anti-clockwise, suppose we are using C2 and C2 inverse.
Yeah.
Okay, this is anti-clockwise, this, oh, okay, this is clockwise, this is anti-clockwise. Okay,
Yeah. Yes, ma'am.
so if we have the matrix, suppose some matrix, then the clockwise and anti-clockwise rotations, the matrix will be transpose of each other. Okay.
Yeah.
Okay, let me write. I'm writing a general matrix for rotation by n. Okay, plus means clockwise along
ZX.
z axis. Okay, so what is the matrix? Cos theta, this is plus sine theta 0 minus sine theta cos theta 0 0 0 1. Okay, this is for clockwise. Now similarly, if I write for anti-clockwise, then it will be cos theta if we derive these two for clockwise and anti-clockwise, the matrix comes out like these. Okay,
Yeah.
so if this is matrix A, what will be this with respect to A?
Summation are same.
Summation are same, yeah, but isn't this the transpose of A?
Mm,
Check yourself. Cos minus sine 0. Here it was a column. Now here you see it is a row. Cos minus sine 0.
yeah. Transfer. Yes, yes, ma'am.
Okay. So
Yes.
for clockwise, if the matrix is A, for the same anti-clockwise rotation, the matrix will be the transpose of the first one.
Yeah.
Okay. Now in transpose, what happens? See the diagonal element. Is it getting changed?
No, ma'am.
No. So diagonal elements are remaining same. And what is the definition of trace?
Summation of diagonal element.
Okay, so even if we take the same, the matrix A or the transpose of matrix A, the diagonal elements are going to be same and their summation is going to be same. So here the trace will be cos theta plus 1, 2 cos theta plus 1. Here also it is 2
2
cos
cos theta
theta
plus 1.
plus 1. Fine. So
Yeah.
actually, this actually gives you a general formula to calculate the trace or the character of any rotation by this Cn rotation.
Okay.
Okay, so suppose if you have to find trace of C3 rotation, okay, so what will be theta here? 360 degree by 3. So you put the value of theta as 120 degree and then calculate, you will get the trace.
Yeah.
Okay,
Okay.
so we got to know that traces or the characters for clockwise and anti-clockwise rotations are equal, and they are because the diagonal element does not get changed even if we transpose the matrix.
Yes, ma'am.
Okay, this one did you do?
No, ma'am. I can't.
Okay, okay, let's see. Transformation matrix for the principal axis of allene. Now I showed you allene where what is the principal axis?
C2.
C2. But where does it pass through?
Carbon atom. 3 carbon atoms.
Yes. So first of all, it is important to know where is the principal axis passing through. So don't take this one or this one as the principal axis.
Yeah.
Okay, so we have the three Principal axis is the, if you have all three C2s or three C3s or like that, then you take that axis which is passing through maximum number of atoms as the principal axis.
Yes,
So
ma'am.
we have okay, now my C2 principal axis is this one. Okay.
Yeah.
Now let me label the, because we have to take the CH bonds as basis. So what we generally do, XYZ we take, but here the basis is this CH bond. Now how many CH bonds are there?
4.
4 CH bonds. So we have 4 elements in the basis. Okay.
Okay. Yeah.
So base in XYZ when we used to take, so we used to get a 3 cross 3 matrix, right?
Yes, ma'am.
But here we have 4 cross 4 matrix. See, all the options are given as 4 cross 4 because we
Yes,
have
ma'am.
4 CH bond in the basis.
Okay.
The order of this transformation matrix is decided by the basis. So if suppose instead of changing this basis, I will take this CC bond, these two CC bond as basis, then there will be
2 by
two
2.
2 by 2 matrix. So here we have 4 CH bonds. Let me number 1, 2, 3, 4. Now you see how these numberings affect the transformation matrix. That is actual the question is. So how we need to know how is it getting transformed. Instead of writing CH1, I am writing just H1. Okay.
Yeah. Okay,
So
ma'am.
it is basically CH1, that is CH bond, first CH bond. H3, H4. Okay. Now, let me just show you again how this C2 works. Okay. See, this one, this one is our 1, H1,
Yeah.
H2, H3,
It's 4.
H4. Okay. Now
Okay.
follow either this side. Just follow this side.
Okay.
What happened?
Upper side changes.
Came to
Upper
the
and
lower
down.
side, right?
Yeah.
Yeah. So if this was H1, it came down
Yeah. S2.
instead of H2. So what we are saying, H1 became H2.
Yes, ma'am.
And if this was H3, see,
S3 become S4.
H3 became H4. So
Yeah.
I can write that H1, it became H2. So instead of this get transformed to H2, H2 get transformed to H1, H3 get transformed to H4,
S4.
H4 get transformed to H3.
Yeah.
Okay, so this is happening. Now this we need to put in terms of matrix.
Okay.
So now my first row, there will be 4 rows, right? 4 rows and 4 columns.
4.
So let's see, this is my column and these arrows denote row. Now my first row is for H1, for the transformation of H1. Now
Okay.
H1 is getting transformed to H2. So I will put a 1 here in the 2 part column is for the transformed part. Okay, and row is for the basis, or I should write transformed basis. This is the initial basis. Okay, what I mean
Okay.
is, suppose you want to see the change of H3, then you have to go in the row number 3. Okay,
Okay.
now now H1 got transformed to H2. So H2 transformed means transformed part will be in the second column because it's the second basis. So that's why in the second column I kept 1, and
Okay.
other columns will be 0
Zero.
because H1 is completely getting transformed to H2. Got my point?
Yes, ma'am.
Yeah. So now you tell me what will be for H2. What? How
One
will this? Yeah.
1000.
Yes, that's correct. So H2 becomes H1. So we'll write 1 here and it will be 0, 0. And H3 and H4?
001, 0001, and
Yes.
0010.
Yes. So others are 0.
Yeah.
Okay. So
Yes, ma'am.
this is one possible transformation matrix. Fine.
Yes, ma'am.
So this is given in the first option itself.
Yeah.
Now the question is asking cannot be a transformation matrix. So this matrix is possible.
Yeah.
So A is not the answer.
Yes, ma'am.
Okay. Now let's see. Now can you imagine that if I change these numbers 1, 2, 3, 4, this matrix is going to be changed.
Oh, yeah.
Okay, are you able to visualize why we put 1 here? Because it was H1 to H2. Okay,
Okay.
if I change this number from, instead of keeping 2 here, I keep 2 here, I keep 3 here.
Okay.
So what will happen? H1 will get transformed to H3.
Uh,
Okay, let me
two.
write again. So now I'm changing my numbering. No one is stopping me to keep the numbering as I want. Okay.
Okay.
So if I keep 1 here, 2 here, 3 here, 4 here, now what will happen? And C2 is the same because principal axis I cannot change.
Can much sure.
So this is C2. Now when I apply C2, these two will get exchanged.
Yes, ma'am. H1 H3.
Yes. And H2 and H4
H2
will get
H4.
exchanged. Okay.
Yeah.
So
Yes, ma'am.
now how the matrix will be? 1 is becoming 3.
Yeah.
So if I write here H1, H2, H3, H4, this is my original basis. This is my transformed basis.
Yeah.
H1 is becoming
H3.
H3. 2 will become
4.
4. 3 will become
1.
1. 4
And
will become
2.
2.
2.
So you see this is different than this one.
Yes, ma'am.
Why the change happened? Because we changed the numbers.
Yeah.
So because of this transform basis has changed, the transformation matrix has to change, right?
Yeah.
Because if we'll use this same matrix, original basis is same. 1, 2, 3, 4 is same. So if I
Yeah.
use this same matrix, I will get this basis, this transform basis.
Mm-hmm.
So I have to change the transformation matrix now.
Yes, ma'am.
Now you tell me what will be the matrix.
0010.
0, 0, 1, 0,
0001.
0, 0, 0, 1. Nice.
Oh, 1000.
1, 0, 0, 0.
0100.
Yes. So you see this matrix is different, right?
Yes, ma'am.
So these two ones were here, and here we have got the opposite side
Yes.
because we changed the basis numbers. Let's see whether this is there in option or not. This is the second option.
Yes, second option is there.
Huh. So is this matrix a possible matrix?
Yes, ma'am.
Yes, that is possible because we did this one. We changed the basis numbers and we got this matrix. Okay.
Okay, ma'am.
Now, so you will ask me till how much I will keep on changing these numbers, right? There can be how many combinations for four numbers?
Mm,
You keep this one fixed and you change these numbers. There will
yeah,
be many possible combinations. Okay. So you don't have to do it that many times. You
yeah.
simply see the transformation matrix. Now let me write C and D1 here. I forgot. 0, 0. Okay. Off diagonal 1. Okay. This is the matrix. Now, what does it mean? Can you now guess? This is for H1. This is for H2. This is for H3. This is for H4. Okay.
H1,
What?
H1 become H4.
H1 become H4. Fine. Okay. Then
H2 become H3.
H2 become H3. Now H3 became H2 and H4 became H1.
H1. Yes, ma'am.
So you see these two are getting changed in pairs. Okay.
Yes, ma'am. H2 and H3.
Yes, and H4 and H1 are getting changed in pairs.
Yes, ma'am.
So this is fine, right?
Yeah.
We cannot change all of them. We cannot change these two across this CC bond. We cannot change.
Yeah.
You got my point. That we can change these two positions only. We can change these two positions only. In this configuration, I cannot make a change from H1 to H2 given the symmetry element is C2.
Yeah.
I cannot change this.
True, ma'am.
Yes. So now here what is happening? It is getting changed in a pair. So this is possible.
Yes, ma'am.
So how this will be possible? See. H1, I'm fixing H1 every time here. H1 is getting changed with H4. So H4 must be here.
Yeah.
Okay. 2 and 3 are getting changed. So this is 2 or this is 3 or this is 3, this is 2.
Yeah.
Okay.
Okay.
So this matrix is possible. Okay.
Yes, ma'am.
So this is possible transformation matrix. Now let's see the last matrix. 0, 1, 0, 0. Okay, this is the matrix, right?
Yes, ma'am.
Okay. Now, what can we deduce from this?
H1 become H2,
H1 become H2,
H2 become H3,
H2 became H3,
H3 become H4,
H3 became H4,
and H4 become H1.
H4 became H1. So is this possible?
No, ma'am, it's not possible.
Why?
There are H1 and H2 and H2 and H3 are not possible for.
Because this is getting transformed in a cyclic manner.
Yes, ma'am.
Okay, all the elements are getting changed. So
Yes, ma'am.
we cannot change in a cyclic manner. We have to change pairwise.
Yeah, okay, ma'am.
There is no pairing. So 1 is becoming 2, but then 2 had to become 1, which is
Yes, ma'am.
not happening here. So what this is doing, so suppose we had 1 here, 2 here, 3 here, 4 here. So what this matrix is doing, it is actually after this matrix, 1 is becoming 4. Sorry, 1 is becoming
One
2.
become 2.
2.
Yeah,
2 is becoming 3. So this was 2, this is 3. Means
it's not possible, ma'am.
this change happened. I cannot
Yeah,
make this change
yeah,
given the C2 operation. Not
sure.
possible. Then 3 became 4, which is okay. Flipping is okay. But 4 became 1. So
It
this
is not
also is
possible.
not possible.
Yes, ma'am.
So this is not a correct transformation matrix.
Okay, the answer is D.
Yes. No, no. The answer is this itself. Okay, you said D. Okay.
D.
Yeah, fine. So the answer is D.
Yes, got it, ma'am.
Yeah. Okay. Okay. So this one is unitary transformation of a unitary matrix always yields a matrix that is diagonalized, real, unitary, or Hermitian. Can you tell this one?
No, ma'am, I think it should be unitary होना चाहिए.
Yes, it is unitary as well as diagonalized also.
Okay.
Unitary, this is okay, right? This has been taught in class
Yes,
that
ma'am.
a unitary transformation of a unitary matrix gives the resultant matrix is unitary.
Yes.
And I derived it last class.
Yes, ma'am.
Yeah, you were there in the last session, right?
Yes, ma'am.
I derived this. Now, this one, let me tell you that what is a unitary transformation? This is a similarity transformation only. Similarity transformation using a unitary matrix. Okay, if suppose I have a given a matrix A, and if I'm using another matrix U for this similarity transformation, okay, this is how we write similarity transformation: U inverse multiplied by A into U. So the resultant matrix, suppose if this is a resultant matrix B, then this kind of similarity transformation is called a unitary transformation. Okay,
Yes,
simply
ma'am.
because we are using a unitary matrix for the transformation, it has a special name of unitary transformation. Okay.
Okay.
Okay, now why do we do unitary transformations?
Mm, no idea, ma'am.
So we do unitary transformation to diagonalize the matrix. Diagonalization of a matrix means of diagonal elements should be 0, and only these diagonal elements should exist. Other things should be 0.
Zero.
Okay. So
Okay.
this is a mathematical method to diagonalize any matrix. There are other methods as well, but this is one of a method. Okay.
Okay.
So similarity transformation to diagonalize a matrix. So do you agree with me that unitary transformation will also diagonalize the matrix?
Mm,
Okay, what is a unitary transformation? It is a similarity transformation. Okay,
okay.
so a similarity transformation was diagonalizing the matrix. So this unitary transformation will also diagonalize the matrix. Do you get my point?
Yes, ma'am.
Just it is just a similarity transformation. Okay, just the name is changed to unitary because we are using this unitary matrix. That's all. Otherwise, it
Okay.
is just mathematically, it is just the similarity transformation. If you use any other matrix, uh, like suppose I am taking a matrix y inverse y is equals to C, then this is what we call similarity transformation. Now suppose by chance if y turns out to be a unitary matrix, then we can call it a unitary transformation.
Yeah.
Okay.
Got it, ma'am.
Yeah, so if now similarity transformation, this resultant matrix, it will be a diagonal matrix.
Yeah, yeah.
Okay, only the
Yes,
diagonal
ma'am.
elements will be there.
Yeah, yeah.
Okay, so it
Okay.
does not matter whether y is unitary or it is not unitary. Okay, a
Yes, ma'am.
similarity transformation will give you a diagonal matrix because it is, this is a method which is used to diagonalize the matrix. Okay,
Okay, ma'am.
so the A option is also correct
Yes, ma'am.
and C is also correct.
Yeah.
So, so now I told you this is a unitary transformation, it means U is unitary. Okay, now it
Yes, ma'am.
is given that unitary transformation of a unitary matrix. Now of a unitary matrix means here A is also unitary. Okay, if these two are unitary, this will also be unitary. This is a
Yeah.
consequence. This has to be unitary. Okay.
Yes, ma'am. Yeah.
Now, if A was not unitary, B need not be unitary.
Yes, true.
Okay. Now, if A is not unitary, we will still call this transformation a unitary transformation or a similarity transformation, anything as which you like. Why? Because the term unitary transformation is not coming because of A, it is coming because of this matrix U, which we are
Yeah.
using to transform.
Yeah.
Okay, so this is
Okay.
it. So here the answer is both A and C.
Okay, ma'am.
I think only A is given.
Hmm.
Yeah.
Okay, ma'am.
Okay. This last question is for you to solve. For an octahedron, the number of C3 excesses are. How many C3 excesses are there in an octahedron?
120-degree rotation.
Yes. So how many such excesses are present? You can think of a octahedron as sum of two
90 degree,
tetrahedrons.
180 degree. One 20-degree to, I think zero is there.
Okay, so this is first part of upper part of an octahedron. So you
Yeah.
can join likewise. Okay, you will get an octahedron.
Yes, ma'am. Yeah.
So the upper part seems to be a tetrahedron, right?
Yeah.
So the number of C3 excesses in tetrahedron, you think,
C4 is there, but C3.
where is C4? Okay, C4
Not of.
for octahedron you are saying. Okay, yes, yes, yes. C for C3. Look through the triangles. Okay, let me show you. Okay, this is what I tried to draw. Okay, now look through the triangles.
Okay. Yeah, yeah.
Got it? So you have to see the two pairs of triangles. One here,
Yes, ma'am.
one here. So how many pairs like that are possible? 1, 2, 3, 4. Fine. 4. That's why I told you to focus on the first part.
Got it, ma'am.
Okay. Through
Yes.
this, through this, through this, and the back side.
Yeah. 4C3.
Yes. So it has 4 C3s. Now let's see if we're checking. Let's see a tetrahedron. This also has same. See, you see the it is passing through these atoms, not
Yeah.
in between the atoms.
Yes, ma'am.
Okay, 1, 2. So it has 4
Four
of
sweet.
these atoms. So it also has 4C3.
Yes, ma'am.
Okay, so the answer is 4C3. Okay, so that's all for today.
Yes, ma'am. Thank
Do you
you.
have any other doubt?
No, ma'am.
Okay, okay, fine. Okay, I'm closing the session.
Yes, ma'am. Thank you.
Yeah, thank you for joining.
Welcome, ma'am.